then we sort of became the local chromosome 16p genome center at that time, because the Genome Project had not yet taken on the global dimensions that it ultimately did. And so we sort of became responsible for developing maps of this region of chromosome 16. First genetic maps and then physical maps of this region of chromosome 16. Narrowed the region down to a region that was about 200,000 base pairs, which turned out to contain 10 different genes, and as luck would have it, it was the 10th one that we interrogated that turned out to have the mutations associated with disease, and that turns out to encode what was, at that time, a novel protein that we called pyrin, after pyrexia, the fever. Now, it turned out that there was a French group that was also competing with us at that time, who fortunately found the same gene and some of the same mutations in that gene at the same time. They chose a different, more erudite name for the protein, the encoded protein, namely Marinostrin, after Mare Nostrum for the Latin, for the Mediterranean Sea. But whether you call it pyrin or Marinostrin, it turned out to be a novel protein. And of course, that was really what we were hoping for all along, was that we would learn something rather than at the end it would turn out to be IL-2 or something like that. And people would say, well, why did you spend however many years it was looking for the IL-2 gene in these patients with FMF? We could have told you that anyway. But it turned out that it was something novel, and it turns out that in fact the N-terminal domain of this protein is a domain that's found in some 20 different human proteins that are involved in the regulation of inflammation and apoptosis. And it is called the pyrin domain, not the Marinostrin domain. And basically, it assumes a 6-alpha helix structure that allows the formation of a dipole. And you can see that the positive charges are denoted in blue here, the negative charges in red. And basically, pyrin domains can engage in cognate interactions with other pyrin domains, just as, for example, death domains can interact with one another in TNF signals. So in any case, in the case of pyrin itself, it interacts with an adapter protein that's denoted ASC, for apoptosis-associated speck-like protein with a card domain, which is why we usually just refer to it as ASC. It has both an N-terminal pyrin domain, which interacts with pyrin, and a C-terminal card domain, which then interacts with the card domain of caspase-1, also known as IL-1 beta converting enzyme. So this is actually the protein that activates pro-IL-1 beta, a 31 kilodalton protein in humans that's the pro form of IL-1, into the biologically active 17 kilodalton form that mediates fever and inflammation. And so then this does put pyrin upstream in that cascade, and at least gives us a beginning of an understanding of how mutations in pyrin might lead to unexplained fever. In any case, it turns out in later work from our lab that in fact the C-terminal domain of pyrin, the so-called B30.2 domain, interacts also with the catalytic domains of caspase-1, shown here, the P20 and the P10. So there are multiple interactions there. And actually, that C-terminal B30.2 domain of pyrin is where most of the disease-associated mutations reside. And so that's really a very interesting thing. And it turns out that if one looks at DNA fingerprints associated with those mutations, that one can deduce probably common ancestors for the modern-day carriers of those mutations. So that, for example, the blue here depicts the M694V mutation, the substitution of valine for methionine at position 694. It's very common in the North African Jewish population. And in fact, that mutation with an associated DNA SNP haplotype is seen in other populations, such as Turks, Armenians, and Iraqi Jews. And there's a fairly large stretch of DNA that's in common amongst them. suggesting common ancestry. Moreover, the carrier frequency for these mutations, and there are several of these mutations for which this holds, is extraordinarily high in Middle Eastern populations, on the order of 1 in 3 to 1 in 5 in those populations, which, given the fact that there are multiple mutations at these high frequencies, really suggests that there could have been something, some perhaps pathogen, that was selecting for these high carrier frequencies over the course of human history. So in any case, and if one models the B30.2 domain, it actually turns out that several of the mutations form a ring around a putative binding pocket for something. So that has been very interesting to us. So what could the selecting pathogen be? Well, we don't know, at least at this point. One speculation that I was discussing with a friend in Turkey a couple of weeks ago is that it might be smallpox. And actually, the evidence for that, although speculative, is at least interesting. So there's been a lot of talk about, well, where did smallpox first arise? It's an obligate human pathogen, and there's at least some archaeologic evidence, for example, that suggests that one of the early places where smallpox arose was probably in the Nile Valley. This is actually the mummy of Ramses V. You can see a close-up that there were these pustules on his skin, and those are at least speculated, perhaps, to have been smallpox, and that he died of smallpox. And this is at least a speculated path of spread of smallpox, and you can see that at least early on is seen in the Mediterranean basin. It requires a fairly high population density in order to maintain it in a population, and there's a very high mortality, which of course would go along with the idea that it could have been selecting for variants at some particular protein. But even more interesting is the fact that pox viruses actually encode proteins with a pyrin domain, not a merinostrum domain, which actually inhibits caspase-1 activation. And this is actually one of the mechanisms by which pox viruses are virulent. And so there would be at least another guilt by association with regard to the pox virus. But whatever may be the case, we have developed knock-in for mutations at the FNF locus, so that perhaps we can look at some of these issues. And so this shown here is a picture of some of the knock-in mice that we have. So these are mice in which we have knocked in the B726A mutations at the FNF locus. You can see the wild-type glittermates are shown here, heterozygous here, but the homozygous mutant mice are small and have skin ramps. If you euthanize these mice, it turns out that they have massive lymphadenopathy and splenomegaly, disruption of the architecture of the spleen. They spontaneously develop arthritis. In fact, if you section the involved joints, they have a lot of polys in the involved joints. When we have looked at these mice in terms of the phenotype and looking at genetically,